If you run exactly one program, the physics are remarkably clean. A single application, talking directly to bare metal hardware, executes with perfect, uninterrupted efficiency. But that is rarely how we interact with machines. We expect to stream audio, download large digital files, and type documents simultaneously, demanding that multiple applications share the exact same physical processor and memory blocks. If you give all those programs unregulated access, their instructions collide. Memory gets overwritten, components starve, and the entire system instantly collapses. To prevent this, we rely on a highly specialized piece of software called the kernel. It is the very first thing loaded into memory during the boot process, establishing itself as the absolute authority over the machine. The stability of your phone, your laptop, and the servers running the internet depends entirely on this invisible layer. It acts as a strict hardware dictator, deciding exactly which application gets access to the physical machine and for exactly how long. This control is enforced through a rigid architectural boundary drawn right through the system. Above it sits an unprivileged user mode for everyday applications. Below it lies a highly fortified kernel mode, which maintains exclusive control over the physical CPU and RAM. Applications are strictly sandboxed in user mode. If a buggy web browser or a piece of malware tries to directly access the physical memory, it bounces right off the boundary. It cannot destroy what it cannot reach. When a program actually needs to read a file or allocate memory, it triggers a software interrupt called a system call. This serves as the only legal bridge across the boundary, passing a strictly formatted request down for the kernel to review. Executing that request requires a context switch. The system pauses the application, saves its exact state, switches down into privileged mode, executes the hardware command, and then returns a result back to user mode. All of that saving, switching, and returning takes time. Operating systems intentionally sacrifice raw computational speed to guarantee mathematical stability and security. Once an application successfully hands control over to kernel mode, 4 distinct management systems immediately go to work behind the scenes. The first is process management. Because a single CPU core can only do one thing at a time, the kernel slices time into microsecond blocks, rapidly scheduling which application thread gets to use the physical processor next. Simultaneously, memory management allocates virtual addresses to each of those programs. It draws strict borders in the physical RAM so that a word processor never accidentally overwrites data belonging to your music player. Then there is device management. By handling the complex hardware drivers internally, the kernel provides a standardized interface. Developers can write code to print a document without needing to know the technical specifications of your specific printer. Finally, file system management translates abstract software concepts, like folders and documents, into the physical magnetic or electrical signals required to actually write data onto a storage drive. Without these 4 tightly orchestrated systems running in parallel, the smooth, concurrent multitasking you rely on every day would be mathematically impossible. The central debate in operating system engineering is deciding exactly how many of these management tools actually need to run with total hardware privileges. The traditional approach is the monolithic kernel, the architecture used by Linux and Unix. In this model, the core services, the file system, and every single hardware driver live in the exact same privileged space. Grouping everything together creates blazing execution speed. Because all the components share the same memory space, they communicate directly, eliminating the delay of internal context switching. But that speed comes with a severe trade-off: zero fault isolation. If a single third-party graphics driver contains a bug, that error cascades through the shared space and crashes the entire machine. The monolithic architecture is a calculated gamble. It achieves raw computational performance by sacrificing system-wide salt tolerance. To solve that fragility, engineers developed the architectural opposite, the microkernel. This model strips the privileged space down to the bare minimum, pushing almost all services and drivers up into the unprivileged user space. This creates supreme reliability through isolation. If an audio driver crashes in user space, it cannot bring down the entire system. However, because those isolated components now have to constantly request permission to talk to each other, the heavy communication overhead causes severe execution lag. The software industry needed a practical middle ground, leading to the hybrid kernel. This approach mixes monolithic speed for core processes with microkernel safety for less critical drivers. Major tech companies aggressively adopted this hybrid model to stabilize consumer computing. Microsoft built their modern NT architecture on this philosophy, bringing it to the mass market with Windows XP. Apple executed a similar pivot. To deliver the stability required by creative professionals, they rebuilt their entire ecosystem on the XNU hybrid kernel, launching macOS X. That specific compromise between performance and fault tolerance is why the vast majority of consumer hardware used globally today still relies on hybrid architecture. The operating systems that run the modern world ultimately settled on a pragmatic balance, achieving both the computational speed the hardware is capable of and the reliability that human users demand. Regardless of whether an operating system uses a monolithic, micro, or hybrid structure, the primary objective remains the same: manage the physical hardware so the application developer does not have to. There is, however, a bleeding-edge exception known as the exokernel. In this experimental model, abstractions like virtual memory and standard file systems are completely stripped away, leaving a core handling nothing but basic security. By giving specialized applications direct, unprotected access to the raw hardware, the exokernel design represents the absolute limit of computing performance, catering only to software built to handle its own resource management. Whichever architectural path is chosen, the kernel functions as the underlying law of the machine, the strict mediator that makes the complex illusion of modern computing a physical reality.